I'll try to speak as slow as possible to make up for 2 sessions. First of all, it's been a while since my last conference speak, so don't be too hard on me. But anyway, my name is Torsten. I'm from the Ostfalia University of Applied Sciences in Wolfsburg, and I will be telling you something about Qt in university education for automotive engineers. First of all, a few words about myself. I studied at the right place where I work right now at the Department for Automotive Computer Science in Wolfsburg. I did my master's in Brunswick or Braunschweig. It's not in Canada, it's the one in Germany. And I used to work for Volkswagen, and now I'm working as a research assistant. And yeah, this is me at the exact moment when I, by accident, deleted the etc folder on our faculty server. So I would recommend it to everybody to have a good time. And speaking of faculty, we are located in Wolfsburg, like I said. We have around 3,500 students. And our faculty of automotive engineering is focusing on 2 departments, actually. The Department for Automotive Manufacturing, which is pretty much the guys who are into crankshafts and suspensions and all that stuff. And the Department for Automotive Computer Science, or as I like to call them, the cool kids on the playground. This is where I belong. And yeah, what we actually do is in teaching, we do software engineering from beginner to advanced level, all the other stuff. So if you're into automotive industry, you know OSEC, AUTOSAR, vehicle connectivity like CAN buses, all the other vehicle buses, and car-to-X, car-to-car, car-to-infrastructure communications and stuff like that. And also embedded systems like hardware engineering and the software part for control applications and stuff like that. And what I want to talk to you, or what I want to tell you today, is actually 2 things. First of all, I want to show you an example where we use Qt to enhance our teaching at our department. And the second part, the slightly smaller one, will be an example where we use Qt to teach UI development itself. And starting with the first one, first of all, a little bit about our philosophy at our department. We always try to not qualify students to be tool experts, because it's like three times a month there's somebody from some big company coming here. You have to tell the students to do data mining. You have to tell them to do AI. You have to tell them to do whatever. Name it, we all got it. And our philosophy is to encourage our students to think in an abstract way. So whatever tool the industry later on is throwing on them, they can work with it, and whatever is necessary, they can deal with it. At least that's the best way when people drop out of our university. But the exception that proves the rule. And since we are on a Qt World Summit here, you can probably guess Qt is one of the exceptions where we use tooling, or we do extensive tooling. And the other one is called MATLAB Simulink. I don't know, is anybody here from the automotive industry and knows MATLAB Simulink? Nobody. Okay, so I prepared a few slides about that to give you an introduction. But in a nutshell, it's a proprietary software by the MathWorks. It's a numerical computing environment and a programming language. And it's the de facto standard in automotive industry to do almost everything. So if you go to an automotive engineer who has nothing to do with computers, you can be 99.999% sure that he knows MATLAB Simulink and that he knows how to push the buttons there. And to give you a small introduction what it is like a way to solve your problems or model your problems in a block diagram way. So you can, like in this example, it's very popular for control loop stuff. You can model your problems there. You can simulate them. You can also generate code from it, run it on a target hardware, and embedded hardware, or you can run it on the computer. But you can also do like other functionalities. You can do like state charts and put like logical stuff in there to do almost anything you want. At some point, it doesn't make sense to do it in a state chart anymore, because I guess you all know from UML and stuff like that how state charts work. But actually, you could do anything with that. And the fun thing is, or the good thing is, when there's somebody who has absolutely no idea about software engineering, he can do pretty interesting things without going through the without going through learning C or C++ or whatever. So we like to use it, and it's like a standard tool in the automotive industry. So our students benefit from it. And like I already said, there is one very interesting thing you can do. You can generate code from these models. Then you can compile it with a standard compiler. There's standard C code coming out of it, and you can run it on a target MCU, like this one from STM. This is one we use very often. It's an STM32F4, so it has a floating point unit and stuff like that. And instead of just using it as a breakout board, we put it in a so-called modular learning platform for vehicle electronics. This is a system made up from different modules you can put together. So these systems really exist in real time, in real life, and they can connect with they can talk to each other via a CAN bus. It's a very popular connectivity bus in the automotive industry. And we have different of these systems. You can see in the middle there's a light systems where students can, or we throw the students in situations where they are the engineers who have to implement the software for a lights ECU. So ECU is an electrical control unit, all these small computers in your car. And we also have other stuff like our alarm lock module on the left side, where you have like 2 buttons to lock the car and unlock it and trigger an alarm. And we also have a windscreen module where we have a little stepper motor on it to act like the windscreen wiper. And this is the actual system in real life. And when students are working with these systems, they come to a point where they say, okay, it's all good. I get a feeling for what we're doing here, but my model or my software gets so complex, I don't really know what it's doing anymore. And at this point, like a debugging system would come in handy, but we go a little bit different way at this point. Debugging is possible, but we introduced them to X-in-the-loop testing. Some of you might heard of it. X-in-the-loop is, the X stands for model, software, hardware. There are other versions as well. And in this X-in-the-loop testing, you put input data to your model and check if it behaves the right way. You can do this automated, or you can do it with with a mock-up of the actual system to test it. And what we introduced to them is the model-in-the-loop testing. So they can take their model before they even put it on a target hardware and test every functionality they got. So what we need is like an input and an output controls for the whole system that looks and feels like the real system. And if you do this in MATLAB Simulink, you end up with something like this. This is from a functionality point of view, this is okay. This is what you can use for something like that. But if we make the connection from the real hardware to this system, it's quite hard to imagine that this is supposed to be the inputs and outputs of the real system. So at this point, Qt comes in handy, because Qt gives us the ability to create an user input-output system, which really looks like the real one and gives the look and feel of the real one. And the only problem with that is there is no connection between Simulink and Qt so far. So we made that up ourselves. And what you need for that is on one side you have the Qt system, where you have the inputs and the outputs. On the other side, you have the Simulink model. So we need some way to get the data from the Qt side to the Simulink side and back from the Simulink side to the Qt side. And we're doing this by propagating the model of our Qt environment. So this comes almost for free, because all our signals or our attributes are registered to the property system of Qt. So we can serialize it into a JSON package, send it to the Simulink side via the local host with a UDP package. And from there, we can do something with the data, which comes out of this block, do something with it here, send it back, or put it in the transmitter block, and from there, it will be sent back to our system. And this actually works like this. This on the left side is actual Qt code running. So we have like a light switch here. When this is going in real time, not as fast as I do it right now, I'm doing a slow motion here. When somebody changed the input signal, the underlying data model will be propagated to the Simulink model. You can see here the light switch position changed to 4. This one will be received here and put on the signal line here. And in the signal down here, it can be processed. Like here, the system will go into the upper beam state and then drive like the output states here. It turns the upper beam state to true and the backlight state to true, and requests to it transmitted this request to update the system, the model, back to the Qt side. And on the Qt side, it can be applied, and then the lights can be turned on, for example. And then it's going to be, because the model changed, it's going to be propagated again. Yeah, and this is, for example, how the system works, and this is something our students implement. And to give you a bigger picture, this is the system our students see when they work with it. It's also Qt code. We have all the systems here. We can move them around. We can skip a few of them. And we can also get them back because I need them right now. In the background, in my ancient Windows 7 machine, I have MATLAB Simulink running, where the actual functionality is implemented. And for example, if I turn on the lights here, you can see, oh, it works, thank God. You can see that the lights are actually going on. And for example, if I turn to upper beam lights, they're also going on. But the whole functionality is not here in the C or QML code. It's all in MATLAB Simulink. For example, when we stick here with the stepper motor, which acts as a windscreen wiper, we can, for example, turn it to on, and you see the windscreen wiper is starting to move. And if we go into MATLAB Simulink and check in here, we can actually see the program running here. So this is the functionality which our students can implement in Simulink, and they get like a visual feedback in via Qt. We can also have a look at the actual data that is communicated. Here's the model that is exchanged via both of them, via Qt and MATLAB Simulink. And here you can see the inputs for the stepper motor going on and off, and that's what actually makes it move. Yeah, and the good thing for us is all these graphics, for example, they're already existing because of the documentation we have to provide to the students. So it's very easy, or it was very easy for us to create this system, and it's definitely a benefit for the students, because as you can all imagine, when you work with an MCU, all the flashing and checking if it's working and so it's very gross. So having a simulation, a needy simulation where you can check everything is a real game changer, like people used to say. Yeah, that's the first one. The second part is the smaller one. It's an example where we use Qt to teach UI development. And our main challenges in teaching is that, yeah, we have to motivate our students. Because in the end of the day, Netflix is our biggest enemy and all the other fun stuff you can do on the internet. So we need something to keep the students hooked. And we have a very simple approach to that. We like to do cool projects with them. And two fellows who help us with that are Mr. X-Wing and Mr. TIE Fighter. And you probably know, or you might know the game. It's called, I don't know if I'm allowed to say Star Wars here, but it's called the Star Wars X-Wing tabletop game, where you have to move these small figures on a table, and you can attack each other and stuff like that. Even though I don't play it, I'm not active in this game. I really like it, or I like the idea. But I thought, you know, I'm someone who's sitting in front of the computer all day. I don't want to move something by hand on the table. I thought, couldn't somebody else do that? So we came up with the idea: couldn't we mount these figures on small robots and let them do it? And then we thought, a table is a little bit boring. Let's just take like a 65-inch touchscreen and let them move on that. And let them let the touch screen be the game master who decides who has to attack and stuff like that. And to give you a short impression how this whole looks like, so this is our table, and because we're in the Star Wars universe, we need some atmosphere, so we need some stars. It's unfortunately not that it's not that good to see here on the big screen, but there's also a video. Here you can see the actual robot moving in circles or in rectangles. And here on the left side, you can see the actual tracking. And the fun thing about this project is it gives us a lot of possibilities. We can teach like tracking algorithms here. This is, for example, actual code running here. To track the robots, it's a 50-point touch screen, so we can track like a lot of robots. And we can all sorts of things with it. But the actual thing we're trying to achieve here is to make the students think that a modern UI system doesn't necessarily have to be a boring widget animation or widget program. For example, if you have a menu, it can also look like this, for example. And if you want to visualize statistics or something like that, it could look like this, for example. And you can do all other sorts of things, like if you want to show the battery lifetime, you can do it like this. So we want to try to encourage students to think a little bit out of the box to get an idea how the user experience of tomorrow could look like. We can also do other stuff like this. And the overall goal of the whole thing is to get the actual game to be running on the screen, which is quite a big task because there's a lot of stuff you have to think about. But that's our overall goal. And our smaller or goal in teaching here is for one, like I said, to encourage new ways of thinking, and the other one is to demystify the whole user interface engineering. Because if you show this to students, they will be like, no way I can do this myself. It's absolutely impossible. I have absolutely no idea how I could realize something like that. And when we show them that actually, to come back to our light switch, that a light switch is nothing more than a vector graphic in Inkscape with different layers and them put it together on top of each other and activating or deactivating them and putting some QML animations on top of it, which is basically like 20 lines of QML code. They come into a situation where they think, I could do this myself. And this is actually the place where we want them. And from that, interesting or great projects start. And I don't know what time it is, but I'm at the end right now. So thank you very much. And thank you. Here, this part, this is actually the real software the students are working with. And in real life, these systems are connected through a CAN bus here, which is connected via the plug up here on the top. And for example, if I press a button here, the lock button, this system has to send a CAN message to all the other systems. For example, the light system in this case has to react on this message by flashing its lights. Oh, it doesn't work right now. It's probably because MATLAB Simulink on the other side crashed or something like that. And the actual thing, it's running. I don't know what's the matter right now. And the actual functionality is implemented here and is implemented by a virtual bus in this case. So here on this lines, the actual data is exchanged between these three systems. So these three rectangles represent the three systems you can see here: the light system, the alarm lock system, and the windscreen system. And the Qt part is actually just a visualization for inputs and outputs of the whole thing, because otherwise, if you wouldn't have this, you would have this here as your visual inputs and outputs. For example, these are lights which would go on if the actual light on the hardware would have to go on. And here, this button, for example, is the button here, and this button here is the button here. So it's, from the functionality point of view, it's okay, but it doesn't really give you the look and feel, which is a requirement, or at least I think it's a requirement, to have the feeling like you're actually working on the real system. And yeah, this here is actually the real system, so it looks very close or similar to the system we got here. And yeah, our students gave us quite good feedback that they think it's way better to do it like this because, like I said, they have like a feeling that it's really it feels more really realistic at this point. Yeah, that's basically it. Any questions?
Not many at this time. Any projects that you're working on that might be related you could ask questions about? No. How many students are using Qt there?
It depends. It's like always, like I said, it's really hard to get people motivated. It's not in the real lectures or it's not included there because they have to be like very. You have to plan them over many years, and it's really hard to get something in there or get like tooling like this in there. So it's more based on extracurricular activities. And right now, there was one student which was heavily involved in the whole system, not in this one, but in the Star Wars thing here. And therefore, like for many other projects, there are like a dozen or something that were involved in Qt development.
Yeah, it's a good amount.
Yeah.
Yep.
Here in this example, it is only virtually connected. It is connected. So this Qt application is connected via a UDP socket to MATLAB Simulink, but we have this system here, all four of them, as real systems as well. And for example, on this system here, there is actually Qt code running on this system, and it's running on a Raspberry Pi 3. And this one is connected in real life. This one is connected to all the other systems via CAN bus. No, it's the official Raspberry Pi display. It's like a 7-inch display, and underneath there is a Raspberry Pi 3, which is running Qt and has a CAN controller to speak to the other three modules. So, but this here, for example, this is not an Arduino. This is an STM32 microcontroller. It's an ARM controller. It's a little bit more heavy than the Atmel AVR controllers used in Arduino and stuff like that. You can do a little bit more with them. They have a floating point unit, for example, which the other ones don't have. Yeah, it's the one I planned here. Actually, it's event driven. So when you change something in the user interface, for example, the light switch, it will change the model, the MVC model in the background, and this will trigger a network manager. We call it the network manager in the program to serialize the underlying MVC model into a JSON file, like the one you can see here. Like I said, this almost comes for free because all the attributes we're using in the model are already registered to the Qt property system. So therefore, serializing the whole thing into JSON almost comes for free. And then it is sent via UDP throughout the local host to the Simulink side. On the Simulink side, it's I can give you a little inside view. It's here in this block here, all the signals are deserialized and turned back into Simulink signals and going through these signals here and can be used anywhere in the Simulink system. So wherever you want, you can use these signals or these incoming data. And on the other side, when you change a signal here in MATLAB Simulink, the whole it will be put into a transmitter block, the signal, and actually this is done. Oh, my mouse doesn't. Okay, this is done here on this side. Here we're taking all the signals we got here on the system, putting them into this block, and this block will also serialize the signals into a JSON, into a JSON file, and send it back via UDP to Qt. On the Q side, we're taking all the signals that got changed. So because it's an update request we're sending here, and update the actual Qt model that's from the MVC part. And then because we changed the model, stuff like this will be animated, and lights and stuff will go on. Yeah.
Okay, thank you. Any other questions? You okay? Okay. Well, great. Thank you so much for that session.